We've poked multiple holes at textbook quantum theory, at the Copenhagen interpretation. This reminds me of a quote by Saul Kripke, who you knew well, who once said that it really is a nice theory. The only defect it has is probably common to all philosophical theories. It's wrong. So what I want to do now is I want to explore a viable alternative. I want to be solutions oriented. So let's talk about an alternative. In 1924, in a paper titled A Tentative Theory of Light Quanta, Louis de Broglie proposed an alternative called pilot wave theory. This is now also known as the de Broglie-Bohm theory or Bohmian mechanics. So let me start with a simple question again. What is pilot wave theory and how is it different from the Copenhagen interpretation?
There's a fundamental difference between the Copenhagen interpretation and Bohmian mechanics. It is this. In Bohmian mechanics, for a system, non-relativistic system of, say, 10 particles, n particles, some number of particles, you take the particles seriously. That's the only difference. Nothing more. Take the particles seriously. Of course, taking them seriously has implications. If you take them seriously, then you take their positions seriously. Since if a particle is anything, it's something that has a position. So take the position seriously. If you take the position seriously, then even if you accept, as you should in quantum mechanics or Bohmian mechanics, that a system of particles has a wave function, that wave function is definitely not the complete description of that system. The most important part of that complete description is left out. You just have the wave function. That most important part will be the positions of the particles. The complete description will consist of the wave function together with the positions of the particles of the system. And what the theory is fundamentally about is how those particles move, the changes of those positions over time. If you leave the positions out, you're leaving out the guts of what's going on. And all you have is the wave function and the myriad mysteries which arrive from leaving out the guts of the description. That's the essence of Bohmian mechanics. Of course, that sort of suggests that the theory Bohmian mechanics has to involve in its equations, dynamical equations, its fundamental equations of motion, more than Schrodinger's equation for the wave function, because there's more than the wave function. There are also the positions of the particles. So you have to have also equations for how the particles move. And you do. And the equation for how the particles move, called the guiding equation, is kind of obvious. If you just know Schrodinger's equation, there's an obvious guess for how the particles should move. In fact, there are basically 10 different approaches about how you might go about making that guess. They all lead to the same equation of motion. So it's really, really obvious. As soon as if a very intelligent person with some mathematical ability, given Schrodinger's equation, and saying that they're also and believing that there are also particles with positions, and wondering what's the theory, how are these particles actually moving, there's an obvious guess for how they should be moving. That obvious guess is Bohmian mechanics. So for a non-relativistic system in particles, it is in fact the case, given Schrodinger's equation, that Bohmian mechanics involves the obvious ontology, particles with positions, evolving the obvious way. Evolving the obvious way is what I just told you. The equation of motion is just the obvious guess. And why is that the obvious ontology? Well, obviously, if you're talking about a system of particles, then you're talking about particles, things with position. So of course it's the obvious ontology. The very way you speak about the system, a system of particles, tells you what the ontology is. So that's what Bohmian mechanics is, the obvious ontology involving the obvious way.
I see the clear distinction. In Bohmian mechanics, you're treating the particle as something physical. Like you said, you're taking it seriously. And instead of the uncertainty around the position, that position is now determined by a framework, I guess, which is the guiding equation or the guiding wave.
I wouldn't say it like that. It's true, but no, that's putting things in the wrong order.
Okay.
The position is determined by what it is. Particles have position. So there's not yet. Now, the future position is determined from the present position by the guiding equation.
Gotcha.
But that's a step further. That's about dynamics.
Mm-hmm.
What determines the position is the position, because particles have position. There's nothing to determine beyond what you have. Whatever you have, pay attention to what you have in the theory. A wave function and particles with positions. And the extra thing is not the pilot wave. The extra thing is the wave are the positions of the particles. Take them seriously. The wave function is the same wave function as in textbook quantum theory. That's not something added. Although a common mistake made in talking about pilot wave theory is that what many people say, oh, it adds this strange kind of pilot wave. That's exactly what it doesn't add. That's just the thing which was there already in the Copenhagen interpretation and in all versions of quantum mechanics, the wave function. What it adds are the particles. The reason that's hard to appreciate is because it sails under the radar. What do you mean it adds the particles? We were always talking about particles. How can you say you were adding particles? Yes, you were always talking about particles, but you weren't taking them seriously. Because if you were taking them seriously, they would have been included in the state description via their positions.
Yeah, I think that's a crucial distinction between the two theories. About one theory, which is the textbook quantum theory, not taking position. There's a lot of uncertainty around the position, whereas in pilot wave theory, you are taking the position seriously. Can you help me?
Let me qualify what you just said a bit. It's not even that there's a lot of uncertainty about the position. If to have uncertainty about the position, there would have to be a position.
Yeah.
So it's a more metaphysical, intrinsic kind of fuzziness than your genuine uncertainty.
Yeah, I agree. Can you help me with the help of the most famous experiment, I guess the double slit experiment? If the position of the particle has been taken seriously, and I guess if there is this fuzziness, has not even uncertainty around the position, if there's a definite position and the future position is being guided by your current state and the guiding equation, how do you explain the results of the double slit experiment? How do you end up seeing that result or that output?
Are you familiar with the picture of the trajectories for the double slit experiment?
I am, yeah.
But we can't show it, right? Here.
I can put it up later.
Okay. So what happens is this. I mean, the particles are guided by the wave function. Therefore, their motion, the structure of the trajectories is affected by the structure of the wave function. When the wave function, which involves a sum of two pieces, a piece coming from the upper slit and a piece coming through the lower slit, when these two pieces start to interfere, so you get an interference pattern in the wave function, that structure in the wave function generates an interference pattern in the pattern of trajectories, so that particles tend to go to certain special places. So conceptually, it's not too surprising that the arrivals of the particles will reflect the structure of the wave function, which after all is guiding the particles. And then if you work it out in detail by looking at the exact equations of motion, you find that you get exactly the predictions of quantum mechanics for the two-slit experiment. And in fact, you also get, by going a step further, the most surprising aspect of the two-slit experiment that Feynman talks about. It's one surprise. But by the less surprising aspect is the fact that a particle which goes through just one slit can somehow, in the orthodox point of view, seem to behave as if it went through both slits and interfere with itself. But the wave goes through both slits, so that's not a particular problem from the Bohmian point of view. On the other hand, another feature, a really surprising feature that Feynman highlights in his discussion of the two-slit experiment, is that however you are able to measure which slit the particle goes through, this must, as Feynman puts it, must force the particle to behave like a particle and not behave like a wave and not exhibit any interference pattern. As soon as whatever you do to find out what slit the particle went through, however gentle it might be, as soon as it gives you that information, it will, ipso facto must destroy the interference pattern. And that's pretty striking. And it's perfectly clear, if you think it through, the whole experimental procedure in Bohmian mechanics, why that must be so. I recommend you try to think that through for yourself. It's a good exercise, but it's true. You fully understand all the things that Feynman highlighted as puzzling in the two-slit experiment. They're perfectly clear in Bohmian mechanics. You just have to do the analysis and think things through carefully.